So let's talk about what a z-score is. So a z-score is something we actually talked about back in chapter 3, and we're kind of using it more in more detail now to talk about the area underneath a normal distribution. So a z-score is a statistical measurement of a score's relationship or distance to the mean. So the way I think about this is how many standard deviations away is a certain value. That's kind of the question it answers. So for example, at our normal curve, if we have the average right in the middle, there's mu, standard deviations at the inflection point, and it goes on beyond there. So if I had a value like right here, that z-score looks like it would be like 1.5, because it's 1.5 standard deviations away. Over here, maybe like right here, this value, maybe that has a z-score of like negative 0.75, because it's 0.75 standard deviations away, it's within 1, and it's on the left side, so that z-score would be negative. And to find these values, you just take the x value, subtract the average, and divide by the standard deviation. So let's take a look at an example of just using some z-scores. So we have a normal distribution here. We have an average of 50, so I'm just going to put that in the middle right away. And this is something that's always really smart to do, is just put your values in right away. So there's 50. I guess this then would be 56. This would be 62. What's happening? And then on the left side, so I guess right here, we would have, that would be 68. Oh, that keeps coming up. And then over here we would have 44. Over here we would have 38, and then here we would have 32. All right, so let's find the z-score for 62. So I'm going to use the formula. So z is x minus the average over standard deviation. If you didn't write that down on the last slide, you're definitely going to want that. So we take the value. So this is our x. So x is just the value we're plugging in. So it'd be 62 minus our average, which is 50, divided by the standard deviation. So the standard deviation in this case looks like it's 6. They give us that, in fact. So that's 6 over 6, which gives us 1. Now that makes sense, because 56 is exactly 1 standard deviation away. So it makes sense that the z-score is 1. For 44, any guesses what that's going to be? My guess is that it's going to be negative 1. Let's try it. So we do 44 minus 50 over 6. That's negative 6 over 6, which is indeed negative 1. Okay, so that z-score is negative 1. So then I say, what value yields a z-score of 1.2? So we know the z-score this time. It looks like our value should be somewhere between 56 and 62. Maybe something like 57, 58, I don't know. Let's find out. So we have 1.2 is equal to x minus the average, which is 50, divided by the standard deviation, which is 6. So I'm going to multiply both sides by 6. Looks like I'll then have 7.2 is equal to x minus 50. And then we add 50 to both sides, so we have x is 57.2. So like we said, is just beyond 56. Our prediction was right. So solving for z-scores is pretty much what your first homework page is, and it's really quick. So you've pretty much got that down now, being able to calculate these. So the z-scores for being exactly 1, 2, or 3 standard deviations away are actually really easy, because remember, the z-score tells you, the z-score, which the formula is, and if you want to put this on the front of your packet, there's a spot for it, x minus the average over standard deviation. And the z-score tells you how many standard deviations away you are. So if we're 2 standard deviations away, what should the z-score be? I think it should be 2, right? Because if we use this exact distribution, which is kind of a special one, say where we have an average of 0, and a standard deviation is 1. So if I do like 2, let's do 2. So I have 2 minus the average, which is 0, over the standard deviation, which is 1. That gives me 2. So it makes sense that if you're 2 z-scores away, or you're 2 standard deviations away, your z-score should be exactly 2, because that's how far away you are. That's all there is to it. So really nice values, and don't forget you can use these with the empirical rule. We're going to learn some harder ways of factoring, some harder ways of finding probabilities today, where you won't be able to use the empirical rule. Because right now all we can do is have these exact values and find the area in between them. But if we have like a value here, and a value here, let's say, and I want to find the area in between, it's going to have to do with finding the z-score, because that's standardized over any normal curve that you have. So let's take a look. So suppose a student can either submit only their SAT score or their ACT score to a particular college. Suppose their SAT score was 550 and their ACT score was 24. Which score should the student submit? So the thing about z-scores is it does a nice job comparing you to, or any data point, to all the other data points. Because it says this is a very good score. That would mean having a high z-score, because that would mean that you're far away from the rest of the data. If it's a lower z-score, that would mean you're not as far away. So let's take a look. So here they say SAT or ACT. Their SAT is 550, so I'm going to do the z-score for SAT. Put a little z SAT. So that's going to be our value, 550, excuse me, minus our value, 500, divided by the standard deviation, which is 100. Looks like that's 50 over 100, which is 1/2. The z-score for the ACT is going to be, let's see, they had a 24 score, minus the average, which is 18, divided by the standard deviation, which is 6. That gives me 6 over 6, which is 1. So it looks like the ACT score would be the better one to submit because it has a higher z-score than 1/2. That's all there is to it. So let's talk about percentiles. Percentiles are the percent of area to the left of a value on a density curve. So basically what this is saying is that you're finding this area right here. So if they give you a value, you have to be able to find that area. And we do that by using z-scores. But percentile is something you might have heard a lot in testing. They say you're testing at the 99th percentile. They make a portfolio like, they make a bell curve like this, and then they figure out how much percentage of the other test takers did you beat. Did you beat 99% of the country, or 98% of the country, or 97% of the country? And then they use a normal curve like this to be able to make that calculation. So there's a kind of an interesting question here that was posed. Can you picture a baby at the 25th percentile for height, but the 70th percentile for weight? So that means that they're among the quarter shortest birth babies, but also they're very high on the end for weight distribution. So this would be a short, pudgy baby. And if you can find a picture of that, then more power to you.